Hello guys, my name is Josh. I'll be explaining to you some concepts that have to deal with oxidation states and understanding the significance of how to determine the charge of each atom and the charge of the overall molecule and the different constituents of that molecule, because that's going to play a major role in naming compounds, and especially compounds that have transition metals in them, because you had to know the charge to determine what type of molecule or how many of each atom is going to be within that molecule. So first things first, let's take a look at the periodic table. So as you can see here with the periodic table, it's very important that we understand where different elements fall in line in terms of their groups and families, because that's going to dictate the set charges that they're going to have. And this will be explained in further slides when we look at the actual rules for oxidation states. But first things first, if you look at the first group with hydrogen, lithium, sodium, potassium, just focusing on the metals, not paying attention to hydrogen. If we just focus on the metals in that group 1, we know that these metals will always have a set charge of +1. And right next to them, the group 2 that contains beryllium, magnesium, calcium, they will always have a set charge of +2. So if you're going to remember anything about the periodic table, it's important that you remember that the first and second group have charges that are going to be +1 and +2 respectively. And then once you look over to the far right, where fluorine, chlorine, bromine, and all the other halogens are, those are typically always going to have a set charge of -1. And as I'll explain during the later part of the video, fluorine will always have a charge of -1. And then in the middle, where the transition metals are, these can have various charges. So they can have charge +1, +2, +3, and that's where it's important to know the charges of all the other elements in the compound, because that's going to dictate what charge you give that transition metal. All right, guys, here's a list of the oxidation rules, and it's very important that you memorize these rules and you understand how to manipulate them for application in different problems that you're going to be seeing during your exam and quizzes. So first things first, remembering, like I just said, group 1 and group 2 elements all have that set charge of +1 and +2 respectively. And then also remembering that there are different compounds or different molecules that also have set charges when they're in compounds, such as silver, zinc, CD, and aluminum. So these molecules, even though some might be in the transitions metals under the periodic table, they only have that one charge that corresponds to the values that you see on the screen. So you'll never see, for instance, Ag2+. It's always going to be Ag +1. Moving on, understand that hydrogen can have two set values. Hydrogen can be either +1 or -1. And that just depends on what metal is what is actually bonded to the hydrogen. So if hydrogen is bonded to a metal such as potassium, it's going to assume the oxidation state of -1. Whereas if it's bonded to a nonmetal, it's going to assume the oxidation state of +1. The reason for this is due to electronegativity. So the more electronegative an atom is, that means the stronger or the greater the affinity it has for electrons. And remember that electrons are negatively charged. So if hydrogen is more electronegative than potassium, that means it's going to pull those electrons closer to hydrogen, closer to itself than it would to potassium. Therefore, hydrogen is going to become more negative, and potassium is going to become positive because it's losing a negative charge. Next thing you have to remember is that fluorine, being the most electronegative atom in the periodic table, is always going to be -1. And any metal or anything that's bonded to fluorine will then be positive. Even though oxygen typically is always -2, because fluorine is bonded to, if you have fluorine and oxygen bonded together, fluorine will assume the minus state and oxygen will assume the positive state, only because fluorine is more electronegative than oxygen. Next thing you have to know is that, again, like I said, electronegativity is going to dictate. So if oxygen is bonded to nitrogen or carbon, it's going to assume the negative state, while the other molecule that's bonded to it is going to assume the positive state. And the last thing that you had to know that I'll explain on the board is that the sum of the oxidation numbers for a neutral compound is 0, and that is going to help you determine what the actual charge of the cation or anion that you're dealing with is, and then the sum of the polyatomic ions, or the charge of the polyatomic ion, is going to equal the oxidation state, which I will also explain. So now moving back to the board, we see that you have the overall charge of this molecule is 0, right? So anytime they just give you a molecule like this without giving you that charge up there, I just drew it in parentheses so that you guys can understand what I mean by the overall charge being 0. So if they give you something like this, you assume that that overall charge is 0, which means that whatever is in the brackets, this sum of the oxidation states of whatever is in the brackets has to equal that of the sum of this plus this has to equal 0. So if we know that this whole thing has to equal 0, that allows us to then deduce what the charge of each different, what the charge of the anion, in this case the anion, and the cation is. Because we know based on the oxidation state rules that, for instance, sodium is a group 1 element, therefore it's always going to have a positive 1 charge for its oxidation state. That means that +1 plus something else has to then equal 0, which means the charge of this is going to be -1, because +1 plus -1 gives us 0. Therefore, if this total charge for the copper and chloride ion is -1, then we can deduce what the charge of copper is, what the charge of copper is, because we know the charge of chlorine. Chlorine is going to be -1, and since we have 2 chlorines, we're going to have -2 for chlorine. So what the method that I want you guys to utilize is set the charge of whatever you're looking for the whole ligand molecule, this whole ligand molecule, you're going to set that charge for it equal to your unknown, which is the metal that you're interested in. So you're going to label that as X plus whatever the charge of everything else is, because you should know those charges, right? So in this case, chlorine is -1, and we have 2 of them, so it's going to be -1, the overall charge of the entire ligand, equals X, our unknown, plus -2. Therefore, X has to be +1, and then our metal is going to be Cu+. So if we come over here and do the same thing, we know that the overall charge of this molecule is 0. Therefore, if potassium is +1 and we have 3 potassiums, that means this overall charge will be +3. And then +3 has to equal 0 if we add something else to it. Therefore, the charge of this entire ligand molecule is going to be -3. So again, we set -3 equal to our unknown, which is X, plus the overall charge of whatever else is bonded in that ligand molecule. So here we have another chlorine. Chlorine is -1, but since we have 6 of them, it's going to be -6. So therefore, the overall charge of the ligand, -3, is equal to X, which is our unknown metal, plus -6. Therefore, X has to be +3, so then you have Fe3+. Moving down here, you see that you have another case where this is -2, right? Chlorine is -1, but since we have 2 of them, that means that this is going to give us a charge of -2. And because the overall charge has to equal 0, if this is -2, then this has to be +2, meaning +2 is equal to our unknown metal, or X, plus, in this case, ammonia has a charge of 0. So therefore, +2 is equal to X plus 0. Therefore, X is equal to +2, and platinum is going to be 2+. So again, it's very important that you utilize this method, because it's going to simplify the amount of math that you have to do and the amount of rearrangement that you have to do. So as you can see here on this slide, we're going to have these summary questions that I want you to try, and I want you to see if you can understand how we're getting that charge and how we're getting the actual metal to be shown here to give us that correct charge. So if you try this problem and you don't get that correct charge, then I want you to come back, rewatch the method that I used to answer all these types of questions, and apply it to that same question to see what's the overall charge? Is it 0? If it's 0, what charges do I know for sure? This is -1, therefore, since we have 2 of these, it's going to be -2, making this whole ligand molecule +2, meaning +2 has to equal the charge of our unknown metal plus whatever else is bonded to it. And in this case, it's 0, so +2 is equal to x, our unknown, plus 0, therefore x is equal to +2. So try that method out, see if it makes sense, and then see if you can answer these summary questions. And if you can, then move on to the next part.